Hi everyone, thanks for joining today. It's my great pleasure to introduce Jiaming Song as today's speaker. He is a research scientist at NVIDIA, and prior to NVIDIA, he was a postdoc at Stanford University. And today he's going to talk about a topic which I think I'm pretty excited about, obviously, because I think it's really a game changer for Bayesian optimization. And I think this talk or this paper, it really correct some things that are maybe a bit wrong in the literature. And with that, Jiaming, floor is yours. Please take it from here.
Yeah. Thanks for having me here. I'm Jiaming. I'm currently at NVIDIA working on diffusion models, and this is obviously one of my only works on Bayesian optimizations, as I don't come from the background. So so let me begin. So today's talk is about a general recipe for likelihood-free Bayesian optimization, but we will go through that, and you can decide whether that's Bayesian enough for us to call it Bayesian optimization. And this is work with me, Lantao Yu, Willie, and Stefano. So again, we care about the task of doing black box global optimization. As you may have known, the setting is that we have a potentially noisy black box function. Let's call it f. And our goal is to estimate the location of this global maxima of f. And this has various useful applications. For example, you can use this to do hyperparameter optimization or neural architecture search, where the input x is the configuration of the hyperparameters, and the y would be some sort of error metric of your neural network, and you want to try to get it as low as possible. And this is also related to tuning of certain systems to get, for example, your CPU balance to be well balanced. And you can also use this for optimizing laboratory equipment and machines, and especially Willie has done a lot of work on collaborating with the Stanford acceleration groups on using these for accelerator policies. And you can also use these for materials discoveries and protocols, and a previous group member of mine used this in strategies for charging electric batteries. So this is obviously quite useful, as you guys know. And basically, the more traditional approach that is different from what I'm going to talk about here, the way to do this is via Bayesian optimization. So the idea is that we have a set of past observations, we call it dn, and these are indexed by xi and yi. So here we assume you have a single return or single value of yi given xi. So from here, the typical way of doing this is via Gaussian process. So we have a couple of observations. First of all, let's assume there's no noise in the observation at first, but you can basically use these samples to come up with like possible, more likely configurations of the function. So for example, if you observe these few points, then you have a better sense of what the function could be under some smoothness prior. And based on this distribution of functions, you can then query at a particular point x, and then you can get the probability distribution of y given x and the dn. And the most popular one, obviously, is doing Gaussian processes, as like when you query x, the distribution of y becomes Gaussian. So what do we use for, what can we get from this Gaussian process? The important thing is that we want to make decisions. And the model basically tells us where we tend to believe there is a higher likelihood to get higher values. So essentially, we want to construct the acquisition function from the model And a lot of the typical strategy is to find the global maximum of this acquisition function, and then we try to query this as our next query point. Typically, a lot of the acquisition functions are defined as expected utility over the model. So here, we assume a utility function. Let's call it u of y. And previously, the distribution of y is given as p of y given x and the existing observations. This may depend on our prior model and our existing observations or likelihood. And although not all acquisition functions can be characterized as such, two fundamental ones can be done as such. So for example, the probability of improvement function, which is essentially the probability of y being over some threshold, let's call it tau, can be characterized by this utility function. So this utility function is this indicator of y being over some threshold tau. And another very popular acquisition function is called the expected improvement. And this is basically it's sort of like a ReLU function if you heard about it. So if y is greater than the threshold tau, then the utility returns the difference between the two. Otherwise, it returns 0. So it characterizes exactly what's the expectation of y being improved over tau. And oftentimes people choose these utility functions such that they have analytical forms for Gaussian processes, and you don't actually have to compute this gradient or compute this integral using, say, Monte Carlo methods. Yeah. So, but as you also may have known, there's typically drawbacks with using Bayesian optimization with Gaussian processes. The first is obviously scalability. The most naive way of doing Gaussian process inference is around O to the n power of cube. So that's basically because you have to take matrix inverse. And even for cases that are relatively simpler for sparse GP inference, you also still have O of n compute complexity for making every next query. And that is without taking into account that you have to optimize the acquisition function itself. The other drawback is expressiveness. So here, this plot shows architecture of a transformer, which is seemingly being used in deep neural network architectures anywhere. But although there are efforts to combine Gaussian process kernels with neural network architectures, it's still less easy to use like models like GP compared to, say, neural networks. So our key question here is that in Bayesian optimization, our query only depends on the acquisition function. So if you think about the entire process as a graphical model, conditioned on the acquisition function, then our query and model are actually independent. So then we are interested in like whether we can do this thing similarly without a separate probabilistic model, basically without all the drawbacks of the Gaussian process inference. So let me give an overview of the methods that we are going to talk about today. So the first category of methods uses models with tractable probabilities such as Gaussian processes. And we call it analytical expected utility because we basically obtain the acquisition function by some utility function which we have an analytical integral. The second category of approaches uses a deterministic model such as decision trees or neural networks that takes in an input and gives you a deterministic output. And this is a classifier-based approach called BO. And as we will show later, this corresponds to the probability of improvement acquisition function. And our method that we will introduce today extend this to all non-negative utility functions through a very simple trick. And we also have the benefit of using the deterministic model. So let's first look at the simpler case. and see how intuitively we can do so-called Bayesian optimization, or maybe black box optimization via classification. And basically here, let's look at a function. And this function has a curve, and the curve contains, for example, 4 past queries. And obviously we don't actually know the f of x when we are doing the queries, but here is just something for reference. And as we can see, there's one point that is slightly higher, and there are 3 points that are slightly lower. So essentially, what we can do is that we can draw a threshold along some quantile. So here, for example, we draw a threshold over the 75th quantile. And there are 3 points that are below the quantile. And we can intuitively associate it with a negative label. So we can think about that being below the threshold is sort of bad, because we eventually want better solutions that are over the threshold. And obviously, this point, we will give it a positive label. And if you train a probabilistic classifier, here I think we trained a neural network with like a reasonable degree of regularization, then you actually get the classifier probability predictions as such. So, for example, as you can see, the probability of being over the threshold is what we are plotting in this graph. And regions around 0 to 0.4 are very low. Regions around 0.8 and 1.0 is also very low. And where the regions between 0.4 and 0.8 are higher, according to our observations given these 4 points. So intuitively, we can use this to take our next query. But before we do that, let's see the mathematical intuition, why it makes sense. So this idea is actually using a very typical trick in logistic regression, or as you call it, likelihood-free inference, or generative adversarial networks. And the idea is basically as such. So suppose that we can draw infinite number of samples from the positive label, and we can also draw an infinite number of samples from the negative label. And so we can actually train a classifier to classify samples from P of X and samples from Q of X. And with infinite samples, infinite compute and capacity, we can actually show that in many cases, you can get a Bayes optimal classifier, which gives you something that's akin to the density ratio, which is P of X divided by Q of X. So what does it mean in our context here? So here, our ratio is the probability of P of X when Y is over the threshold, and over P of X when Y is below the threshold. It might sound a bit strange to you guys, because here we haven't really talked about what P of X means, but it will be clear in a second. So if we have this ratio, assuming that we got this from this Bayes optimal classifier, then what would be the probability of improvement? So basically, what we do is we can apply Bayes rule. So the probability of improvement, which is basically the probability of over the threshold given X, is here at the first step, we do Bayes rule. We have P of X given Y bigger than tau. And here we multiply by P of Y bigger than tau, obviously. And then we divide by P of X. So this first step is very straightforward. It's just Bayes rule. The second step is also quite straightforward. So on the one hand, we know that we are interested in acquisition function over X. So we're searching for all the values over X. So P of Y bigger than tau is simply a scalar, like a bigger than 0 scalar function that does not actually affect our our optimization, does not affect its maximum with respect to X. And the second part is basically you decompose P of X as the sum between P of X and Y bigger than tau and P of X with Y smaller than tau. So basically, eventually you will get something that's closer to this. And you don't have to take this exactly, but the idea is that when R is larger, then this probability of improvement is also larger. So intuitively, you want the ratio that's over the threshold to be higher than the ratio that's lower than the threshold. And here, yeah, we do not care about X if you're only caring about maximizing this acquisition function. Well, we haven't used it yet, but if we want to maximize it, we don't really care about this value. And the other question is like, maybe like, how did we even define P of X? So it might seem that, you know, it doesn't make sense if you're drawing from some distribution that you haven't even defined. But we actually find that this is also a question when we were reading the earlier Bohr paper. But our conclusion is that because we only care about the density ratio, so as long as you have like some distribution P of X that covers the entire query space, it doesn't really matter. So mathematically, the way we characterize this was we define the decision-making process as a Markov chain, and the distribution, the stationary distribution is the density is going to give us this P of X. But it really, you can switch to another P of X and you can get the same thing. And this is the idea behind this paper called the Bayesian Optimization by Density Estimation by Lewis Tell et al. And it's actually a quite interesting paper, and I recommend you guys check it out. So this is basically the intuition how this algorithm works in practice. In step one, we can see that we have 4 points and we are going to make the next query. And our classifier takes the curve, tries to estimate the probability of what's the highest of being over the threshold. So here, taking the argmax of that classifier, we can see that we will select this current query that is marked as this red star here. And in the next iteration, we have the past 5 queries as the starting point. But now we have more information about this middle region between 0.4 and 0.6. So our classifier will give us values that is give us predictions where sorry, the probability of being over the threshold is higher around this region between 0.7 to 0.75. And we will take our next query here at this start. And continuing repeating this process, we can actually find queries that are basically around this global optima. So now that we saw one successful example of the idea, sorry, what is the problem with this idea? So a very obvious problem is that here, once this point is over the threshold, we don't really care about by how much we are over the threshold. So suppose we have 2 like artificially created instances. So in this first instance, we have 20 query points that are here sampled like uniformly. And we draw a threshold, I think it is at the 50th percentile. So there are 10 points that are positive and there are 10 points that are given negative labels. And the way we did the classifier was that we give every point that's over the threshold a positive label 1, and every point that's lower than the threshold a negative label of 0. So this basically give us the weights, or the classifier weights, that's sort of like this. So in these points, as long as you're over the threshold, every point has a weight of 1. But now let's consider another function. And suppose that our actual function looks like this, but the query locations are still the same nonetheless. So all the function behaves identically when it's below the threshold, but the function behaves differently when it's above the threshold. So what we did here is that we swapped the 2 modes in this function. And so that the global optima appears on the left mode instead of the right mode. So if you did the classifier trick, then you actually find out that, okay, because all the points, regardless of which mode it is in the mode or not, is still over the threshold. So our decision will be the same, or this entire classification problem is identical in these two very different functions. So because the classification problem is the same, then we should expect our queries based on this is the same. But obviously, this is not a desired approach. So while you can solve this by sort of saying we can shift the you can shift the threshold up and down. So for example, if you shift the threshold up to higher and include less points in positive, then of course you could resolve this particular issue. But we are interested in cases where we can get more principled approaches to any utilities. So one of the interesting statements that we have in our paper is that the method that we discussed earlier, which is the Bayesian optimization with the density ratios, or called BO in short, is actually only equivalent to the probability of improvement only. The characterization of the definition of improvement is also a bit hard to characterize, given the fact that in this case, you're using a neural network or like a deterministic function, a classifier. And in the traditional Gaussian process case, you're using a Gaussian process model. Intuitively, we define this equivalence by the behavior at the case where you have infinite samples. So in the asymptotic case, so you remove all the effect of like having the model. So if you all use the same type of model, then if you apply BO and then or you apply probability of improvement, they will give you the same function, and we will have experiments to back it up afterwards. And interestingly, BO themselves took this claim from another paper that is very famous in right now. As far as I've seen, it has thousands of citations now in Europe's 2011, and basically their claim was that the density ratio is equivalent to expected improvement, and which is obviously not probability of improvement. So to just one slide to show where they might have oversimplified things a bit much. So first of all, what they did was they claimed that you define the probability of px given y as this case function, like this step function essentially. So they said that the p of x given y is some function L of x if y is smaller than the threshold, and it's g of x if y is greater than the threshold. This works if you're defining p of x given y smaller than some threshold. But here you are actually defining the function over a particular y. And by Bayes' rule, it's actually just p of xy divided by p of y. So it is not actually a constant function for a range of y values. So if you're smaller than y, p of x given y, this function still depends on y. So you can't just characterize it with one function or another function. So this is where they oversimplified things. And if you assume this is true, of course, then you will get the expected improvement being equal to the probability of improvement, which is what they would get. And this is the proof that they took in their paper. Obviously, I'm not going to let you guys read through it, but if you guys are interested in checking out offline, then this part is where they didn't get it correctly. So because you cannot assume p of x given y is equal to some particular L of x, then this particular equality, which does exactly the same, doesn't hold. And everything before that and everything after that should be reasonable. So then after we talk about the interesting properties of using the classifier approach and its connections to probability of improvement, then we are interested in asking the obvious question. So how do we correctly deal with the expected improvement? And hopefully we can also use this to deal with other utility functions, as we will show later as well. So the solution is actually quite simple. So instead of like giving all the positive queries the same weight, we simply reweight the positive queries by its utility value. And here the utility value is, we assume is non-negative. So if you're over the threshold, you will have a positive utility value. And if you're below the threshold, you have a 0 utility value. And for expected improvement, this becomes the maximum of how much you're over the threshold versus and 0 if you're below the threshold. And this case actually resolve our previous toy example in the sense that now if you have the mode on the right, then this utility function or the weights will characterize how much you are over the threshold. So it will upweight or upweight the points that are further up in the threshold inside this classification problem. And vice versa, if your mode is on the left, then it will give higher weights to points on the left. So in this case, you can obviously see that the classification problem makes a difference, and intuitively it should prefer locations where you have higher weights, because that's where we are trying to bias our problem on. And the harder question is like, why is this correct? So the solution is quite simple, and it's quite obvious that this does not only apply to the expected improvement, but to any utility function. So the idea is actually quite related again to likelihood-free inference and to GANs. So if you know about FGAN, then this is probably the trick that you commonly see in the literature. So basically, the idea is that we use a trick to estimate this integral. So here, the integral is obviously this expectation of the utility function. And we are trying to use our optimization problem here, optimizing over this value x. So here, let's assume we are just taking a particular x. So this is a scalar value. And we are optimizing for a particular x, which is also a scalar that is non-negative. And this objective function may seem quite unwieldy, but basically we on the left-hand side, we have an expectation over P of y given x as well, but there is a utility associated with it. On the right-hand side, there is something else. But basically here is where our weights of using u of y as the weights emerge. Here, u of y is the utility function. F of s, pardon me for reusing the notation here, but here's this f divergence usage of the f function. Here we assume it's a strictly convex function with third order derivatives, and f star is the convex conjugate. And the proof is actually quite simple. You just take derivative with respect to s and you check its second order derivatives. And that will tell you that this function is concave, and the maximum point happens at this integral. So the implication of this is that you don't of course, if you have infinite samples, then you don't actually have to take this trick. You just take the integral directly. But the interesting part is that you can actually take finite samples and estimate the gradient of this objective function on the right, and still get an unbiased gradient estimate to this particular location S. And we can actually use particular instances of F. And previously we said F can be a lot of things. But in fact, we find that when F takes this form, you can actually get reduces to classification function, where this objective basically becomes you have samples from your data set, from your past observations. And on the left-hand side, you are trying to maximize the probability of X where the utility is greater than 0. And on the right-hand side, you try to minimize the utility for everyone. And we also tried different types of F, for example, the ones associated with squared loss, and which would make it closer to linear regression. But we have to admit that we didn't get as good results as we did in classification. So intuitively, this part corresponds to positive label, and this term corresponds to the parts with the negative label. But there's still one difference between our approach versus Bohr, even in the probability of improvement. So here, we actually might create different copies of the pair even in the same data set. So we will first, let's say we will split the data point into two parts, and we'll create two copies of the same data point. And at one copy, we will always give it a negative label, and this will have weight 1. And in the other copy, we will check whether it has a utility greater than 0. Then if it has a utility greater than 0, then we will give it a weight as that is the utility. And if the utility is exactly 0, meaning that they're below the threshold, then we will give it utility 0, or equivalently, we ignore it. So in principle, this approach will work for any non-negative utility function. But we usually, to stabilize training, we usually do some trick to normalize this utility function. But that is still equivalent nonetheless, because we're merely multiplying a scalar value to everyone in this utility function. So the changes to this with respect to Bohr is actually quite simple. You can sort of change it in quote one line without doing the previous data pre-processing. So in PyTorch, you can just add the weights when you're doing binary cross entropy classification, and in other frameworks like Keras, Scikit-learn, or XGBoost, you can also just assign the weights as the sample weights. And as we said, negative points have a weight 1, and positive points have a weight that's associated with the utility function. And our statement is that our approach here we call likelihood-free Bayesian optimization. Again, the likelihood-free component comes from the fact that we heavily inspired from likelihood-free inference, or binary classification approach of getting density ratios. And although here we are not exactly taking a density ratio, but for any type of integral, the Bayesian optimization part is trying to connect our approach to some existing thing in Bayesian optimization. But if you're very dogmatic of the term, we can also say this is just likelihood-free black box optimization. But the connection with Bayesian optimization is that asymptotically, this approach will converge to the desired acquisition function. Again, by asymptotically, we mean that if you have infinite samples from this your search space, and it covers everywhere. Of course, in practice, we are not going to take this. We're not going to have infinite samples. The problem would be trivial if we did that. But in practice, we will have to rely on some prior to help us decide where to search for the next step, which is absolutely needed in zeroth order black box optimization. And this, in Gaussian processes, you use this prior function or the kernel. And in this case, we use the prior that is associated with the classifiers. So this is how we connect each other. The prior are different, but the likelihood function, as you can say, are sort of this similar. So in the first experiments, we will try to establish the validate our theory and show that LFBO, our approach, is indeed correct. So suppose that we have some kind of a ground truth function or distribution that is noisy observations. We can form noisy observations. And here we don't have a Bayesian optimization like strategy. We just take random locations uniformly at random. We're just trying to validate our previous statements. We can compute the ground truth probability of improvement and expected improvement for a particular threshold, because we know what the P of y given x is. We just assume it's a Gaussian. Or we can compute this with the Bohr approach, which is the traditional, the simplest classification approach, or LFBO, which is the slightly complicated weighted approach. So you can actually see that here on the top, you have the acquisition function associated with the ground probability of improvement, which is ground truth. And this is the expected improvement, that is the ground truth. So here we computed analytically. So they are, ground truths. And on this diagram, you can see the behaviors of the Bohr, which is the classifier, the LFBO, which is our approach associated with the probability of improvement, and LFBO, which is associated with the expected improvement. And as you can see, like around 100 samples, you already see roughly similar shapes of these with respect to the ground truths, but BO has the same shape as the probability of improvement, which further establish our point that it's more related to probability of improvement than the expected improvement. And in our case, we can choose probability of improvement or expected improvement, and it will converge to the two different ground truths acquisition function as we respectively. And here's the behavior of the functions when we have a lot of samples, like 10,000 samples. And as we can see, our I think here we use the neural network. Our neural network function converges to ground truths or decently. So on this second setting, we are using this for hyperparameter tuning. And so here we are just using this on this HBO benchmark, where the input I recall was like categorical. So this makes it slightly trickier to apply Gaussian processes in an ideal way. So, but with standard classifiers, they can deal with discrete data quite easily. And here, the shallower plots show that using the BO, which is the original classifier method, using different classifiers. So here is a multi-layer perceptron. That's this one. The second one is gradient boosted trees, and the third one is random forest. So all of these are basically classifier models that gives you a point estimate. And as you can see, that our approach are the corresponding dense curves. And here we are trying to optimize this so-called immediate regret. This is slightly different in the sense that here we are basically following the prior work that the queries are actually stochastic. So given the same neural network configuration, you can have a stochastic result. But the regret itself is computed with respect to our current like return, which is stochastic, versus the minimum possible average value. So let's say if I somehow query the point that is surely at the best configuration, but we got lucky, so we got even like lower than this average like low global optimum, then we will have sort of an immediate regret of something like close to zero or even smaller than zero. And this is an approach taken by the earlier like BO paper, so we didn't want to change that. But even though it's quite strange in like drawing these curves. But the conclusion we want to draw from here is that our approach by switching from the probability improvement to expected improvement, we have obviously improvement over the previous approach. And it also improves significantly over other methods, such as Gaussian processes, which we spent a lot of time on trying to make it work. So these are the classifier-based baseline. And these are the cases where we are in our cases. And you can see with the same architecture, we outperform the original case respectively. And in this second case, well, these are the more concrete results from different HBO bench problems. And we can draw similar conclusions as we had with the first plot. And this is a neural architecture search experiment. And here, I think we are trying to search for configurations for CIFAR10, CIFAR100, and the ImageNet. And again, we can draw similar conclusions that LFBO performs better than BO by switching from probability improvement to expected improvement. And apart from some like exceptions like SMAC, we basically beat like both competing methods. And finally, I want to talk about the case where we can potentially use this for some more complicated cases, for example, in a composite function. So the composite function setting is as such. So instead of having a black box function that gives you one value, we have a black box function that gives us a vector of values. And our objective to optimize for is a known function of this vector value. So, so here, for example, if we have a target configuration called Z star, and our black box function will give us different configuration z, then our objective to maximize for is the negative distance between z and z star. So we are basically trying to find the z that has the minimum Euclidean distance with z star. And here we have the black box function give us a vector. And in this case, this is also quite common in the sense that our black box function does not only give us just one value, and also that's not the only value that we're trying to optimize for. This is also a huge difference. So obviously, we can solve this by using the traditional BO approach. So we ignore all the structures internal to the black box, and we just optimize f of x directly with Gaussian process. But unfortunately, this will become very, inefficient. So for example, if you don't have a black box, then you should just take gradient descent with respect to this function, which should be much faster than if you just did entire black box optimization. So having this additional chunk of information in the composite, which is called in the composite case by some people, is definitely very helpful. However, with Gaussian processes, you first have to define a Gaussian process over this entire vector z, and then try to compute the corresponding acquisition function, for example, expected improvement over this f of x, which is itself a function of z. So it becomes more complicated to do this, and you will, so it's no longer tractable in the easiest case for expected improvement or probability of improvement. So typically the way people do is that they use stochastic gradient descent when they're optimizing at the acquisition function. However, this type of approach is actually quite easy to implement with LFBO, and I'll show how we can do this here. So the idea is that we want to design, for example, a neural network, and this neural network is regularized by our existing information called Z. So here, we have this neural network, let's call it h theta of x, which outputs a vector that has the same size of Z. And so essentially we're trying to minimize this distance to the, we try to minimize the distance to the observed Z. So it's sort of like additional regularization that we add on top of our original classification objective. And the second component is like, once we get this Z, we can use our existing known knowledge about f and h. So which is basically this f of x. Here it's just taking the Euclidean distance. So in some sense, we can design our classifier logics based on the Euclidean distance. And this will give us a classifier. And even though this might be a crude approximation, we basically are trying to make some trade-off between having our function to be like representative of many cases versus like being able to having more priors and being able to optimize faster. And surprisingly, well, or maybe perhaps not surprisingly, by introducing this prior information into our neural network, we are actually able to get significantly faster optimization using much less queries. So in this curve, this characterizes the regret when we are making queries. And we first initialize with 10 queries, so it starts at 10. And the top the more shallower curves are the Gaussian process approach and our approach when we are just purely using this task as a pure black box function. We don't use the information about the black box at all. And in the second set of curves, the darker curves are the cases where you're using composite Gaussian process and composite LFBO. So where you assume that you already know there is this semi-black box or composite structure. And you can obviously see that by using this structure, you have much better query efficiency. And another thing we want to note is that when we are doing the experiments, we find that our algorithm is much faster to optimize compared to the composite Gaussian process case. So we compared with the author's official implementation and find it to be faster to like for each iteration by around at least like one order of magnitude on the same hardware. So to summarize, we show that it's in the Bayesian optimization procedure, you mostly care about the acquisition functions. So instead, you can actually use the classifier models to serve as acquisition functions, which could be useful in a lot of cases where getting a good kernel is hard, such as hyperparameter tuning or neural architecture search. And our distinguish our work from the previous LFBO work, which also used the classifier models, we extend the case of probability of improvement to any desired acquisition function constructed by expectations, simply by reweighting according to the non-negative utility functions. And if you're interested in further details of our work, you can check out our project website as well as the code release, which should contain all the experiments. Yeah, thanks.